Prosthetic legs have allowed millions of people to enjoy a better quality of life by enabling them to walk and run again. But unfortunately, only prosthetic legs provide this sort of functionality, since the legs are not usually required to make complicated movements. That's why other prosthetics that try to replicate upper body parts are not practical, since they cannot execute the dexterous movements that our arms and hands do on a regular day-to-day basis, such as writing, picking up, or holding objects. Amputees have a purpose for prosthetics. They cannot be used by people who are paralyzed due to spinal cord injury or neurodegenerative disorders such as ALS, since they don't have the ability to freely move their body anymore. And in the United States alone, there are more than 5.4 million people that are affected by a form of paralysis, and more than 1.6 million people who are amputees. In order to improve the lives of millions of paralyzed people and amputees across the world, one solution would be to pursue the development of brain-machine interfaces, which can control prosthetics or exoskeletons through the thoughts of the user. In order to understand how a brain-machine interface works, we can split it up into three parts. First are the electrodes that record the signals that are produced from the brain. Second is the decoder, and the last part is the closure of the loop through visual feedback. Currently, we can record brain activity in two ways. The first method requires placing electrodes on the scalp. This is called electroencephalography and is non-invasive, therefore very convenient. But one drawback to this is that the recorded signals are hard to read since they are so small due to the skull being in between the electrodes and the brain. The second method requires placing electrodes on the surface of the brain. This is called electrocorticography, and this yields very accurate and easy to read signals. However, this method does require brain surgery, and the electrodes need to be replaced periodically. The second part of the brain-machine interface is the decoder. The decoder is basically a complex mathematical model that extracts certain features from the recorded signals and translates them into actions. This information is then sent to the prosthetic, which executes that action. The last step is to close the loop so that the brain-machine interface continuously takes brainwaves and translates them into movements. The way the loop is closed is through visual feedback, which means that the user sees the movement being executed, which triggers specific signals in the brain telling the brain-machine interface that has successfully completed the action. Now, in order to make brain-machine interfaces practical, researchers are changing their approach. Previously, they would not allow the brain to develop its own motor map that is associated to a particular brain-machine interface. Because of this, the user would forget how to control the prosthetic every time the computer was unplugged. In order to fix this issue, they do not recalibrate the decoder, and they also give time for the user to learn how to control the prosthetic. Doing this lets the brain create a unique motor map that is responsible for controlling that specific disembodied device.